Hey everyone, and welcome to This Explainer. Today, we are taking a seriously fascinating journey into the very stuff that makes up our world. We're going to start with our most basic, everyday observations of the objects around us and scale all the way up to the advanced engineering paradigms that literally define modern civilization.
Okay, let's just dive right into it. Do me a favor, take a second, look up from your screen, and just observe the objects around you. Have you ever actually stopped to wonder why a tennis ball is made of something completely different than, say, the glass window in your room? It sounds like an incredibly simple question, I know. But the answer to that question is the entire foundation of how we build our world.
And humans have been asking this question and shaping materials for specific jobs literally since the dawn of history. We can actually see this in ancient texts. For instance, the traditional Indian text, the Rasaratnasamuchaya, explicitly points out that if you're making a crucible, which is a vessel that has to withstand extreme heat to melt things, you use clay and iron. Our ancestors just inherently knew that you can't use just anything to hold molten metal. You have to have the right material for the job.
So here's our roadmap for this explainer. 1. The stuff around us. 2. How we group materials. 3. The three major families. 4. Defining material properties. And 5. Ages of material science. Section 1. The stuff around us, focusing on matter and volume.
As a quick baseline, we all know everything around us is made of matter, right? That's anything occupying space or volume and having mass. But in the engineering world, when we talk about a specific type of matter that's used to create an actual object, we call that a material, and it's pretty versatile. A single object can be made of one material or a combo of several, and a single material can be used to make tons of different objects.
Moving right along to Section 2, how we group materials based on their classification properties.
So, to make sense of all this, we need a way to organize things. We call this classification, and we do it based on shared properties. It's exactly like walking into a grocery store. They keep all the spices in one aisle and all the grains in another, right? Well, we do the exact same thing with materials in science. We look for those common characteristics. One of the most obvious ways we classify a material is simply by how it looks. Specifically, is it lustrous or non-lustrous? Materials with a shiny surface are lustrous. Think of metals like iron, copper, or gold. On the flip side, non-lustrous materials just look dull, like paper, wood, or a piece of rubber. But hey, keep the old saying in mind. All that glitters is not gold. Sometimes a dull material is just coated with a super thin layer of plastic or wax just to make it look shiny. Building on that, let's talk about how a material feels. We generally group materials into hard and soft. If you grab a metal house key and try to scratch a surface, you'll immediately find that things that are easily compressed or scratched are soft, like a rubber eraser. Things that are tough to scratch are hard, like a stone. But remember, hardness is totally relative. A piece of rubber is definitely harder than a kitchen sponge, but it's way, way softer than a chunk of iron.
Section 3. The three major families: ceramics, metals, and polymers.
Now this brings us to a massive reality check in engineering. Almost all solid materials fall into three broad buckets: ceramics, metals, and polymers. And if we look at everyday beverage containers, we quickly realize there is absolutely no such thing as a perfect material. Think about it. A ceramic glass bottle is great because it's transparent and keeps your drink fizzy, but it's heavy and shatters if you drop it. An aluminum metal can is super strong and easy to recycle, but you can't see through it and it dents easily. And a polymer plastic bottle, well, it's cheap and lightweight, but it actually lets the carbon dioxide slowly escape over time. Engineers have to weigh these exact trade-offs every single day. Section 4, defining material properties, structure, and performance. Okay, pay attention to this part because this right here is the central paradigm of material science and engineering. It is a strict, linear story of cause and effect. Step 1 is processing. How you process a material entirely dictates Step 2, its internal structure at the atomic level. That structure then determines Step 3, the material's properties. And finally, those properties completely control Step 4, the real-world performance of that material when it's put to use. You literally cannot skip a step. When engineers are pinning down that third step, the properties, they're looking at highly specific mechanical metrics. They're testing strength, which is just the ability to resist breaking under a load.
They check elasticity, which is how well it snaps back to its original shape after being stretched. Conversely, there's plasticity, which is its ability to permanently bend or deform without actually snapping. And of course, they measure hardness against scratching and corrosion resistance against things like acids and gases. To see how these precise properties translate into mind-blowing performance, let's look at barium titanate. It's a very specific type of ceramic. Because engineers perfectly understand its internal structure, they know it has this wild property called piezoelectric behavior. Basically, it can physically convert sound into electricity. Because of that one highly specific property, its performance application is critical. We use it to build the transducers inside high-end audio equipment. Which leads us perfectly to Section 5, the ages of materials science and the history of civilization.
You see, materials aren't just something engineers tinker with in a lab somewhere. They are quite literally the foundation of human civilization. It's so fundamental that historians actually define entire eras of human history by the predominant material we were able to control. We started in the Stone Age, relying on naturally hard stuff. Then we figured out how to smelt metals, kicking off the Bronze Age, which eventually gave way to the Iron Age with even stronger, more durable tools. But for almost all of this history, our control over matter was pretty much just trial and error and alchemy.
And that brings us to, right now, the modern era. We are living in the Silicon Age. We aren't just scavenging for materials anymore. We are actively designing them from scratch, using our knowledge of how atoms behave. Driven by advanced semiconductors like silicon and gallium arsenide, and paired with insane computer simulations to predict properties before we even make them, we have unlocked technological power that our ancestors couldn't even fathom. So as we wrap up this explainer, I want to leave you with a provocative thought. If our mastery of stone, bronze, iron, and now silicon defined our past and our present, what exactly comes next? With the explosion of engineered nanomaterials and crazy advanced biomaterials that can actually interact with living human tissue, what revolutionary material is going to define the next chapter of human history? Thanks so much for joining me on this exploration of the materials all around us. Keep looking closely at the world. I promise you, there is incredible science in literally everything you touch.